All right, so can you tell us a bit about who you are?
My name is Mohammad Naraghi. I am a professor in Department of Aerospace Engineering in Texas A&M University, and I'm involved in teaching and research here. My teachings are about courses that have to do with uh, materials and mechanics of materials, and my research is also about that.
Mhm. And so why do you want to become an aerospace engineer?
Good question. Um, the main reason was I wanted to work on something, do research on something. Well, I wanted to be involved in research, not an ordinary job. And that's because I wanted to be able to decide what I work on. So that's why I became a professor in a research active university. But now why I became an aerospace engineer? Because I was looking for a field in which materials with certain properties are highly desired. For instance, in aerospace, we care about high performance materials because we want materials that are very light but very strong. And so I saw my background matches that. So that's why I went towards this discipline.
And why did you specifically pick nanomaterials as your prior research?
Good question. So part of trying to do, so when I started doing research, it was around 2005. And so I saw nanomaterials as an as an opportunity that hasn't been exploited nearly enough. So it was a material that a range of materials that can have impact on can make things but can help us make better things. Better could be lighter, stronger, tougher, or multifunctional materials. So I saw nanomaterials as an enabling tool towards that end.
Mhm. And let's get into some of your research. So what are graphitic carbon-based multifunctional nanomaterials?
Good question. So let's start with graphite. Graphitic comes from the word graphite. So graphite, as you can see, just a pencil, the tip of a pencil. So it's a layered material. What I mean by that is if you could take a graphite and look at it, zoom in, zoom in, zoom in, and look at it with very strong microscopes, you see layers that are on top of one another. Each layer is one atom thick. So, and these are carbon atoms. They're bonded together. They make very strong bonds with each other. And so, and that like an sp2 bond. So there are three, each carbon atom makes three bonds with three other carbon atoms, and those are very strong bonds. And so, and very stable. So because of that, they're very strong. Now, the bonding between the layers is not as strong, but within each layer, the bonding is very strong. So then, but it also has other properties. For instance, electrons can pass through this layer very easily, and many other interesting properties. So then, now, when I say graphitic, means materials that are partially have this structure. They can have also other microstructures in them. So the whole idea of graphitic nanomaterials becomes things like carbon nanotubes, carbon nanofibers, graphene nanoplatelets, and a host of other things that have this sp2 structure, that have those desired properties. And then the focus on multifunctional nanomaterials, graphitic carbon nanomaterials, is basically how I can exploit this microstructure to generate added value. For instance, can I use it to generate fibers that are very long but very strong for composites in aerospace applications? Can I make composites that are conductive? Because I want not just load bearing, but also conducting electricity. And many other things, like can I make a composite that can have some sort of quote unquote sensing? For instance, when you touch it, it generates electricity. When you deform it, it generates more electricity, and you can use to get some feeling, some understanding of the state of deformation that the material is in. So that's what this whole research is. So basically, we're talking about three aspects: how I can change the how I can process a material to change its microstructure, and the microstructure is changed so that I can get certain properties out. So basically, processing gives me microstructure gives me performance, and the research is how can I change the processing so that I can get the desired microstructures that would give me the desired performance. That's what whole this research is about.
And so now, how can a bio-inspired composites improve the current existing non-biological composites?
Excellent question. So I do less on bio-inspired, but I tell you my take on it. Let me start with this example. Ceramics are very brittle materials, okay? Now, if you look at abalone shell, you'll see it's more than 90% ceramic. It has very little biopolymer in it, like some proteins in it. But still, it acts like a very tough and strong material. It doesn't act like a ceramic, although it's 90% ceramic. And when you dig deep into this and say, why is it behaving this way? Why is it composed of 90% composed of ceramics, but it acts much better than ceramics? That's where the idea of bioinspiration comes into mind. So in what way is this microstructure unique in nature, and how can I exploit that to in the realm of engineering to make better materials? So in bio-inspired nanocomposites, you look at these odd features of nature materials, you try to understand them, try to develop models around it that would allow you to understand why they behave in the certain way that they do, and then you try to replicate that with engineering materials, and you try to do that so that you can get even better materials. For instance, because abalone shell doesn't survive at high temperatures, it's made by nature to survive much lower temperatures. But if I need a composite in aerospace that can go to much higher temperature, can I use those principles? And instead of the ceramic that nature uses, and instead of the polymer that nature has used in abalone shell, I put something else, and I get a material that is very strong, very tough, but it also works at high temperatures. So that's where that bio-inspiration is all about.
Mm-hmm. And can you explain some of your work in experimental nanomechanics?
Good. So like, if I go back to that graphitic nanomaterial, so I mentioned to you we have three things: processing, microstructure, and mechanics. But I'm sorry, processing, microstructure, and property. Now, property can mean many different things. It could be mechanical properties, it could be electrical properties, it could be magnetic properties, thermal properties, all that. And each of them is a vast field. But the nanomechanics in particular is saying, when I go from processing to microstructure, how does that microstructure change the mechanical properties? That's the question it wants to answer. So it's a subset of that broader question. But then, now the challenge becomes, if I want to test this material this big, I can put it in a tension test machine and just break it and see how much load it takes and do my characterizations. But if this is only 100 nanometers thick, And just as a reference, our hair is probably, it's in the order of 60 microns thick. So if this was 100 nanometers, which is roughly about over 500 times the thickness of a strand of a human hair, how would you test it? Because you have to be able to grip it, you have to be able to stretch it, you have to be able to measure forces that are in the sky. So it introduces a whole new set of challenges. So in experimental nanomechanics, one of the things we're doing is, in order to understand the relationship between processing, microstructure, and mechanics, we focus on this part and we say, how can I measure the mechanics given the peculiar features of my sample that's very small, very tiny, and it takes much less force to break it, and so on and so forth. So that's what that subject is all about.
Can you also explain what electrospinning of polymeric nanofibers is?
So electrospinning is a way to make nanofibers. Okay, the process is rather simple. Imagine this is a needle. I fill it with some polymer solution. Polymer solution can be a very simple thing. Imagine polyvinyl alcohol, you dissolve it in water. Okay, so you load it in this syringe, and here you put a target. Target is just a piece of metal. And you apply a high voltage between these two, about 30, somewhere between 10 to 30 kilovolts. This polymer solution here will be charged. Charges are induced in this, and it's going to be pulled towards the target. As it moves towards the target, the solvent on it evaporates. Imagine you come out of the pool, you're wet, and you start running, you get dry because the water evaporates. Same thing happens here, but much faster, because this guy has much higher surface per unit volume, and also because it's going much faster, like say 20 meters per second or something. As it travels towards this target, the solvent evaporates, and some other things happens, like bending instability. It's a little bit more advanced. I don't think we want to get into details of that, but I'll be happy to explain it. But at the end here, these nanofibers form on the target. Now you can have a whole list of syringes here, or sources of polymer, a whole variety of targets, and they control the morphology of the nanofibers you get, and they control the diameter of the nanofibers you get, and so on. So it's a technique to make polymeric nanofibers, which can then be used when you couple it with some other techniques, such as carbonization, can be used to make those graphitic nanofibers that I mentioned to you.
So what has been your toughest accomplishment so far?
Say that again.
What has been your toughest accomplishment so far?
I'm sorry, I dropped, I couldn't hear. My what?
Toughest.
Oh, toughest.
Yeah.
Toughest accomplishment. Good question. The toughest one. Toughest, you mean the hardest to achieve?
Hardest.
I guess I think my toughest accomplishment was, we had a project with the Army, and we were trying to develop some nanocomposites that have some damping characteristics, can damp vibrations. And I say it was the toughest because we failed and failed and failed until we learned how to do it right. So I think that was it.
Mm-hmm. So to high schoolers like me and younger generations that want to become aerospace engineers, what would your advice be to be successful in this career?
Oh, that's a very tough question. Okay, I tell you my perspective on things, and it's what I will tell my, this is what I think I will tell my children when they grow to that age. Although I may change a lot between now and then, but so at least as much as I'm projecting into the future, I think what I will tell them is that it's very difficult to predict what the job market will look like in 5 years from now, 10 years from now. So then it means that the best thing for him or her, son or daughter, is to be able to change. Now, change doesn't mean that entirely, but so then what does it take? I guess part of the change is not being fearful about learning new stuff. But then also there are some things that keep repeating themselves in different subjects. For instance, math, for instance, physics are things that if you want to be in engineering, the foundation of all of them is like math and physics, So I would definitely emphasize that aspect a lot. Now and then I would also highly recommend communication skills, improving on communication skills, written and oral. Those are very important. More specifically, my suggestion is when you go to undergrad school, try to gain some research experience and broad research experience. Broad, research is going to be focused, but different semesters get involved with different professors and different disciplines to see where your passion is. Yeah, that is what I think I would suggest.
Well, thank you for joining me for the interview, and that was great.
Thank you. Best of luck. Again, I'm sorry I was late.
No, that's all right. And have a great rest of your day.
Thank you. You too. Bye.